So we're going to move on to our final video on moments, and that is looking at the idea of tilting. So when a rigid body is on the point of tilting, and we'll see a question say that it is on the point of tilting about a given pivot, the reaction at any other support or the tension in any wire or string, that will depend on the context of the question, is 0. So if I just look at the diagram that we've got on the page here, and we've got a beam resting on two supports. It has its weight acting downwards and it's on two supports A and B, so it's got the reaction at A and the reaction at B. Now if I apply a force to this end of our beam, what's going to happen is if I applied enough force, then our beam, think about it like a seesaw, our beam would pivot at this point A, so it would be lifted off the second support if that force there is great enough. When we're talking about something being on the point of tilting, we're talking about that force being the exact amount of force required before this starts to lift off the support B. So on the point of tilting, we're saying any more force being applied would then cause the rigid body to start to tilt and it to be lifted away from the support at B. So if a force is applied so that the rod is on the point of tilting at A, like we've just talked about, then the reaction at B is equal to 0. So right as it's about to tilt and pivot around A, the reaction at any other supports, so the reaction at B, is going to be equal to 0. So we've got a couple of examples now where we're going to have a look at that in action. So a uniform beam AB of mass 45 kilograms and length 16 meters rests horizontally on supports C and D, where AC is equal to 5 meters and CD is equal to 9 meters. So we've got that in our diagram there. When a child stands at A, the beam is on the point of tilting about C, and we're being asked to find the mass of the child. So just filling out the information that we've got for the moment, we've got the beam had a mass of 45 kilograms, so that means its weight is going to be 45 G newtons, and since our beam is uniform, that weight is acting through the center of mass, which is the midpoint of our beam. So if that beam had a length of 16, the midpoint is going to be at 8, so I've got a distance here. If that's 5, this is going to need to be 3 meters. Also, if that's 2, this distance here would have to be 6 meters, just to make it so it's 8 meters away from each side. We've got the reaction at C and the reaction at D. So that's our sort of initial situation based on this information in the first sentence there. So when a child stands at A, the beam is on the point of tilting about C. So when our child is standing at A, we don't know the mass of that child, that's what we're trying to find, but the child's weight will be mg, so that has now been added to our diagram. And in addition to that, the beam is on the point of tilting about C. So if it's on the point of tilting about C, that means the reaction at D must be equal to 0 newtons. So that reaction at D is equal to 0. So now I only have, well, I've got the mass, which is unknown here. I've got the reaction at C, which is unknown. So what I can do, I can't use the fact that it may be an equilibrium because I don't have this and I don't have that, but I can take moments about the point C, because if I take moments about the point C, then the moment of this force is going to be 0 because there's no distance from the point itself. I'm left with only one unknown. Since this is also 0, that's going to allow me to find mg. So if I take moments about C, then in the direction which is going anti-clockwise, I've got the force this way, mg, multiplied by the distance 5. So I've got 5 mg, and that is going to be equal to the moment going clockwise. Again, this was the only anti-clockwise moment because, of course, this reaction at D was equal to 0, so 0 multiplied by that distance would still be 0, so that's why that's the only one going anti-clockwise. I've got, in the clockwise direction, 3 times 45g, so 3 lots of 45g. So that 5mg must be equal to 3 lots of 45 is 135. So 5 mg is equal to 135g. Since g is on both sides, that cancels quite nicely. So that leaves me with 5m equal to 135, which then tells us that m is equal to 27. So we've got that the mass is equal to 27, and we'll put our units there, 27 kilograms. We have one more example that we are going to have a look at. So our second example, we are told that a non-uniform rod AB of length 10 meters and weight 40 newtons is suspended from a pair of light cables attached to C and D, where AC is 3 meters and BD is 2 meters. When a weight of 25 newtons is hung from A, the rod is on the point of rotating. Find the distance of the center of mass of the rod from A. So we're given a question with a non-uniform rod. We've not been given a diagram. We've got our rod being suspended from cables rather than being lying on some supports. So we've got a few different parts in our question. So let's start just by drawing out that situation. So we've got our rod of length 10 meters. So our rod there has a length of 10 meters and weight 40 newtons. So if I just call this end A and that end B, it has a weight of 40 newtons. So we've got 40 newtons there. Since our rod was non-uniform, we don't know its distance from the end. That's what we're being asked to find. So I will call this distance here X. We were told that the cables were attached to C and D, where AC was equal to 3 meters. So I've got a point C, which is 3 meters from A, and BD is equal to 2 meters. So I've got a point D somewhere here where that distance is 2 meters. Now, since these cables are being used to sort of hold our rod in place, it's being suspended there, there is a tension in each of these cables. So I've got a tension at C and a tension at D, and these are going to act like our reaction forces did in the previous examples. So we were told that a weight of 25 newtons is being hung from the rod, or hung from the rod at A, and at that point it's at the point of rotating. So at A, I'm going to add a weight of 25 newtons, and if it's on the point of rotating, if we think logically, if this is being suspended and suddenly I add a weight to this side, what's going to want to happen is if I'm adding a weight to this side, it's going to end up tilting that way. So if it's tilting in this direction, the pivot, if you like, is at C, which means it is the tension at D, which is then going to be equal to 0 newtons. So our tension at D is equal to 0. So now, if I take moments about C, then again, the reason I'm taking moments about C is because that's one of the unknowns there. So if I use the fact that that's an unknown, now that I have my moments about that point, the distance to that point is 0, so the moment of this is going to be 0, so it doesn't matter that I don't know the tension at C. What I can do is, if I take my moments going first of all in the anti-clockwise direction, I've got 3 times 25, so 3 times 25, and that is equal to the moment in the clockwise direction. Again, since the tension here is 0, I didn't need this moment there because multiplication by 0 is just going to give me 0. Now the force times the distance here, I've got 40 as my force. The distance from here to there, if this entire distance was x and this distance here from A to C is 3, what is remaining must be x minus 3. So I've got 40 lots of x minus 3. If that's 3, this must be x minus 3. So now 3 times 25 is 75, and that is equal to, if I expand out this bracket, 40x subtract 120. So 40x subtract 120 is equal to 75. I can add my 120 to both sides. So 40x is equal to 195. And then I can divide through by 40, and that's going to give me that x is equal to 4.875. So our final answer is going to be 4.875 meters from A. That is the distance of the centre of mass of that rod from point A. That's the end of this video. Thank you so much for watching. For more A-Level and GCSE maths content, like and subscribe to N Jackson Maths on YouTube.